So this is question 1b of the 2016 Probability Distributions exam for level 3 of NCEA. That was a mouthful. Question 1bi is to make sure that it's bell-shaped and that you've marked in the standard deviation lines. Remember, there should be 3 of them each side of the mean, and the way that works is that we know that around about 99.7% of the area under a normal curve lies within plus or minus 3 standard deviations of the mean. So basically most of the visible area will lie in those zones. And so if you structure your curve so that it looks like the curve is almost at 0, almost touching the horizontal axis when you get to this point here and this point here, then and we've got a smooth curve leading down to that, then that's pretty good. Of course, well, technically, the normal curve never actually reaches the horizontal axis. Never actually reaches 0. It's called a horizontal asymptote. And it's unbounded, meaning it actually goes on forever. Gets closer and closer to that horizontal axis, but never actually touches it. And so I've just shown that by making my blue line visible right at the extremes. So as long as you had something like that, had the mean in there, had the standard deviation marked in there, that was fine. So on to part 2. Using this model, that's this model here, calculate the probability that 2 different randomly selected shoppers both spend more than 40 minutes at the supermarket, and give any assumptions that you need to make. So 2 different. Whenever we're asked to calculate 2 different events, the easiest way is to start by calculating one of them. So solving a simpler problem first. So using this model here, I want to calculate the probability that one randomly chosen shopper happens to take more than 40 minutes. So I should start by writing that down, being clear what I'm finding out. Okay. And I'm going to do this using a graphics calculator, which is really what you should be using in this exam, because the exam is written really assuming that people have them. So it's a disadvantage if you don't. So menu, statistics mode, distributions, normal distribution, NCD. Remember how that works. NPD you never use in this course, so it's either NCD or inverse. The inverse one is when you're working backwards, when you've been given a probability and you have to find a particular value on the x-axis. So this is just a regular problem. We're finding a probability, so we're going to use NCD. The lower bound is 40, and so we should always shade what we're trying to find out. And because in theory the normal distribution actually has no upper limit, that means that we put for our upper value just a really big number, because our calculator obviously can't put infinity in, and it won't matter once we've got a really big number. As you can see, that curve gets so close to 0 that it doesn't really matter if I put another 9 now or not. I'm going to get the same answer. Standard deviation, what was it? It was 10.8. We were told that in the question. And the mean was 32.5 minutes. And execute. And the answer is 0.2437. Now, I'm not going to round that at all. I'm going to write everything on the screen there. And the reason is because in principle, you shouldn't really round until your final answer. In this case, if I'd just given it as 0.2437, it probably wouldn't have actually changed my final answer noticeably, but it's just a good principle to leave your rounding until the end. So now, that is the probability for one randomly chosen shopper taking longer than 40 minutes. I want to know the probability for 2 different randomly chosen shoppers taking more than 40 minutes. How do we do that, do you reckon? Just pause the video and have a think about it. Have a guess. Well, it turns out we square it. We square the probability for 1. Okay, like so. And we get 0.05939 to 4 significant figures. Okay, Now, why do we do that? Why is it that we can square the probability for one shopper, do you think? Because it's really important that you understand this. Don't just memorize it, you need to understand it. Probably an easy way to think of it is to think of a simple example of when you toss a coin twice and you get heads or tails. And so there's a 50% chance or 1 in 2 chance of getting a heads. And getting heads again, the second time, is half again, isn't it? Or a quarter. So there's going to be probability of getting heads twice. So tossing a coin and getting heads both times is going to be 1/2 of a half, or 1/2 squared, which is going to be a quarter. So there, it's the same situation where in order to find out the probability of the event happening twice, we just square it. Okay? And if you think of another example, if you tossed a coin and then you rolled a dice and you were interested in getting heads and then getting a 6. So, like this, then what would you do? Well, your probability of getting heads would be 1/2, and then probability of rolling a 6 would be 1 in 6. So the probability of both happening, both rolling heads and a 6, would be found by multiplying them, because there's a 1 in 2 chance of getting heads and a 1/6 of that again of getting a 6 as well. So you could say it's 1/2 times 1/6, or 1/6 of a half, which is going to be 1/12. So whenever we're looking at two events both happening, we can multiply them on one condition. What's that one condition? Well, you think about these two examples, tossing the coins and the dice. They are independent events, right? The result when you toss the coin the first time is independent, or has no effect on the result when you toss it a second time. Similarly with the dice. And so therefore the probability of rolling that 6 is independent of whether we've rolled a head or a tail. So we can only multiply those probabilities if we know the two events are independent. And so here we've been asked for any assumptions that we're making. Well, the assumption is that the time taken by the first shopper is independent of the time taken by the second shopper. So this assumes that the time taken by the first shopper is independent of the time taken by the second shopper. So multiplying those probabilities or squaring it depends on that assumption. If we look at the marking scheme for that, and here it is. So it was for merit, this question, and to get merit you needed to calculate the correct probability. You also needed the assumption of independence, and it had to be in context. So you couldn't just say the events were independent, you had to say that the time taken by the first shopper is independent of the time taken by the second shopper. Okay, on to part 3. Okay, so moving on to part 3. Following an observational study of shoppers, the supermarket has changed its model for the time shoppers spend at the supermarket. For this new model, the supermarket has kept the same mean, same as the old model, but has adjusted the standard deviation. Using this new model, the percentage of shoppers who take longer than 40 minutes is estimated to be 31.1%. Discuss how the standard deviation of the new model for the time shoppers spend at the supermarket compares with the standard deviation of the old model for the time shoppers spend at the supermarket. You may wish to refer to your answers in parts 1 and 2 to support your explanation. Notice how it doesn't say anything here about calculate. It just says discuss, compare, and then it says explanation. So that's a clue that they're not actually wanting us to necessarily calculate anything for this question. And you could actually waste a bit of time if you did. So this is all about comparing. What do we know? We know that the new model has the same mean but a different standard deviation. And we know that the probability that a customer takes more than 40 minutes in the shop is now 31.1%, whereas it was, what was it before? It was only about 24%. So that's risen. Okay, so let's write that down. We'll start by writing down what you know straight away. Gets you started. So we know that in the original model, the probability that a customer spends more than 40 minutes was 0.2437. Was 0.2437. Whereas in the new model, the revised model, this probability has risen to 0.311. That's this figure here, 31.1%. Okay, so that's what we know so far. And we also know, remember, that the mean has stayed the same, but the standard deviation has changed, and we know that probability has increased. So what should we do next? Well, the next thing I would do is I'd make it visual. So I'd go back to the model itself that we drew before, and we can see the yellow zone is the 24.3%. Now that's gone up to 31.1% without the mean changing. So in the new model, the mean has stayed the same, but the standard deviation has changed. Do you think the standard deviation must have grown or shrunken for that yellow zone to become bigger? I want you to pause the video and I want you to have a think about that. Okay, I'm going to use red pen here, which you shouldn't do in the exam. I'm just doing that as a teaching tool so we can see what's going on. In the exam, always stick to black and blue because the red and the green are the markers colours. But it might be that it does something a bit more like this. So that the shaded zone, the zone over 40 now, represents a slightly bigger proportion of the new red model than it did of the old blue model. Okay, so for that to happen, for the distribution to get wider like that, what has to happen to the standard deviations? Remembering that there will still be three standard deviations, each side of the mean is still going to contain most of the area under that curve. So if the standard deviations come out like that, then that could work, couldn't it? So 1, 2, 3, something along those lines. So in order to now have a greater area to the right of 40 without the mean changing, then the amount of spread and therefore the standard deviation must have grown. Distribution has got wider and greater variability. So let's write that down. So in the original model, the probability a customer spends over 40 minutes was 24.37%, whereas in the new model it's risen to 0.311, 31.1%. So as this probability has risen, it means that the area under the curve to the right of 40 has also risen. For this to happen without the mean changing tells us that the standard deviation must have increased. Now, we need to put this into context. So what does that mean in context when the standard deviation increases? Well, it means greater spread from the mean. And in this situation, it means the times spent at the supermarket must vary more under the new model. So let's write that. So this means greater variation in shopping times. So we've stated the obvious about the probabilities changing. We've interpreted what that's saying in terms of the curve, and then linked that to the standard deviation, and then we've put that into context by saying it means greater variation in shopping times. Really important that we have that context in there. Okay, if we look at the marking scheme for that. So, on to part 4. Part 4 says discuss one potential limitation with using a normal distribution to model the time spent at the supermarket. So this is now talking about context and thinking, okay, so how might we expect the true distribution of time spent shopping in a supermarket to differ from what we see here? I'd like you to pause the video and I'd like you to think about the last time you went shopping at Countdown or New World or Pack and Save, and I want you to think about what would you expect. How long do you normally take in the supermarket? How long do your parents take? How long do other people take? So think about how that distribution might actually look. Think about some things that might depend on as well. So just pause the video, have a think about it, and I want you on a bit of paper to please sketch what you think that distribution would look like. Okay, so what must be the left-hand end of that distribution? What can we not go below? We obviously can't go below 0. Okay, so anything to the left of there, I need to rub out. So that's already different from this model, isn't it? Okay, what will most people do? When most people go shopping, what would be a time that would be longer than most people would take? Well, most people are going to take within 30 minutes most of the time, aren't they? You're going to get a few people that just go in and out just to get something that they need, like just to get some Coke and chippies, or just to get something they forgot to get last time. So you're going to have quite a few people close to 0. Like, you know, it might take only 5 minutes or so. I mean, you've got to go in there and queue. So then you might have something like this. And then what's going to happen after 30 minutes? Well, you're going to get a few people that spend ages shopping, right? Now, is there any clear upper limit for how long you can spend? No, there's not really, within reason. I mean, you can't stay there after it closes. So we might get a bit of right skew happening. So you're going to get something like this, or it might be, you're not going to get a symmetrical shape, are you? So the key thing here is that there is a lower bound at 0, whereas a normal distribution doesn't have a lower bound. And if you notice that new model that we did in the last question, did you notice what was really weird about that? It now gave quite a, well, you could see it was going to give quite a sizable proportion in the negatives. And of course that can't happen. So that's a limitation of the model. Okay, so let's write that down. So let's start by talking about what we would expect the true distribution to look like. So in reality, the true distribution of shopping time spent at the supermarket will have a lower limit of 0, whereas a normal distribution model is unbounded. That means it goes on forever, like we talked about before. So that's a limitation. And they only asked for one. Other things you could say, well, I would expect a bit of right skew or positive skew, because most people will spend less time shopping, or 30 minutes or less, whereas a few people will spend a long time shopping. And obviously you can't go less than 0. There's a floor effect. Can't go below the floor. So true distribution may be right skewed, not symmetrical, as most shoppers will probably spend 30 minutes or less, but a small number may spend a much longer time. Okay, so we've compared what we would expect the true distribution to look like for shoppers in the supermarket with the way the normal curve behaves, and we've put that in context. So let's look at the marking scheme. So parts 3 and 4 we kind of marked together. We already talked about part 3. Part 4, it says a very small proportion of shoppers are modelled to spend less than 0 minutes at the supermarket. That's using a normal curve, which is not possible. There should be a minimum time to spend at the supermarket. And based on the time to walk from the entrance to the checkout, the time spent at the checkout, which is not set when using the normal distribution as a model, as the normal distribution is unbounded. So we sort of talked about that too. Mirror, you had to describe a potential limitation with the use of the normal distribution and link this to this feature to the context. So you had to link it to the context of shopping times. For excellence, same thing. But the different thing at excellence, you had to get the previous question right about the standard deviation getting larger as well. So you needed both of those things. Whereas merit, you just needed one of those things. Okay, in the next video, I will get into question 2. Ciao.